Okay, so welcome. Today's lecture we will be talking about the application of what we've been discussing last week to mechanics, both in the Lagrange formalism and in the Hamilton formalism. But before we get to that, I'll just finish up a little bit about the stuff from last week that I did not have time to finish. Let me just say before we start, I have been looking at the homework problems, and I want to make one general comment because I saw it in several of the solutions. A common argument for the angular momentum being a pseudo vector was that that when you make a total inversion, essentially, so when you send x to minus x, or if you want send ei to minus ei, that a pseudo vector a vector changes sign under this, while a pseudo vector does not. This is not the general. This is a very typical argument to see, but it's not a super general statement in terms of in terms of what defines the pseudo vector representation, and it's only valid in an odd number of dimensions. So, for example, you can imagine, like in 2 dimensions, if you send e1 to minus e1, e2 to minus e2, then the corresponding determinant for that transformation is +1, not -1. So this is actually a rotation, not an improper rotation. You can see this if you take x and y, you can rotate that without making an improper rotation to the y prime x prime axis, right? This is just making a rotation by 180 degrees. So this is a proper rotation, actually, just changing the sign in an even number of dimensions. What is the definition of the pseudo vector representation is that rather than having a vector mapping to AV, that you have so this is the vector representation, that you would have this mapping to the determinant of A times A then V. So this is what defines the pseudo vector representation. Now, of course, for an odd number of dimension, this the determinant of minus the identity is -1, so that is an improper rotation. So for an odd number of dimensions, the determinant of the negative of the identity, that's equal to -1. So that is an improper rotation. And if you set A equal to minus identity, then the determinant of that times minus identity, that's equal to identity in an odd number of dimensions. So that's why if you have a pseudo vector in an odd number of dimension, when you make this total inversion, it does not change sign. Whereas in an even number of dimensions, you cannot make this argument. So that about that. So to continue with what we didn't have time for last week, we talked about integration on manifolds. We talked about integrating essentially P forms. You can integrate them over a P-dimensional region. I wanted to mention that if you have a Riemannian manifold, so if you have a metric on your manifold, there's a natural volume form. So there's a natural n form, so to say, in n dimensions. There is a natural n volume form. If there is a metric. And in order to see that, well, if we have an n form, right, in n dimensions, it's a one-dimensional space. We've discussed that, right? Because there's only one way of choosing n of the coordinates. It's choosing all of the coordinates and then wedging them together. So you can imagine you can say epsilon here equal to dy1 wedge up to dyn, right? But this thing here is not necessarily equal to, if I change my coordinates to dy prime 1 prime, it's not necessarily the same as this, right? We'll take an example later. So in general, this is not the case. So I'm going to take this now, and I'm going to try to figure out, I mean, this will be a basis for the n forms wherever I am. So a general n form let me write it omega, or whatever. I used omega in the lecture notes, so let me use it here also. A general n form, it's going to be some function f multiplied by epsilon, right? Where f is a function. So I want to figure out what is the natural value of this function f, so that I get kind of what I would like to have. So the task is to figure out what f is. So if I choose now, so choose an orthogonal coordinate system. Okay, what does that mean? Well, it means that all of the coordinate directions are orthogonal to each other, so all of the off-diagonal elements of the metric are equal to 0. So I can just call GAA, the diagonal elements, they are equal to the square of the length of, so there's no sum here. This is true for every A. So this would be the length, where LA is the squared length of the basis vector dA. But if you have if you want to know the volume of the of this cube in coordinates that is spanned by these orthogonal coordinate vectors? Well, it should be, right? So if I write here like the1, the1, the2, the3, so if this is a block like this, all of the angles here are right angles, then the volume of this should be this length times this length times that length, right? This should be the length. So the volume spanned by these coordinate basis vectors should be the product of all LAs, right? But this is equal to the square root of G bar, where G bar is the determinant of the metric tensor. So this means that if I want omega here to be the volume to represent the volume, then I should have this relationship, right? d1 up to dn equals to this product, to this square root of G bar. But if I insert this into that definition, well, this epsilon, just taking these coordinate differentials, slamming them together with the wedges, I plug d1 into y1, I get 1, and so on. For every one I plug in, I get 1. So the epsilon here of this d1 through dn is equal to 1, so I'm only left with f. So this must be equal to f. So indeed, this means that the natural volume element is the metric determinant, the square root of the metric determinant, times this epsilon. And in fact, it turns out that this epsilon, if I define epsilon through the coordinate expression in each coordinate system, it turns out to be what is called a tensor density. It's not really a tensor. It's a tensor density in addition to transforming with the typical tensor transformation laws. It also has a factor of the Jacobian determinant, which is exactly this square root of G bar. And this square root of G bar in front actually makes this into a tensor. So this is kind of the natural volume element in an n-dimensional manifold with a metric. So just to take an example of that you're familiar with, let me take R2 in polar coordinates. So from Cartesian coordinates, you know that the natural volume form should be dx wedge dy, right? That's just because they are orthogonal and they are affine coordinates. So that's the volume form everywhere for Cartesian coordinates. Now I can express here, okay, that did not want to work. I can express dx. So let me just write that x is, of course, r times the cosine of theta. Y is r times the sine of theta. So I can express dx here by taking this differential as the r cosine theta minus then r sine theta. The theta, that's just taking the differential. Same thing for dy. It's dr sine theta plus r cosine theta d theta. And if I wedge both of those together here, what I get is that this omega expressed in polar coordinates, that's going to be r dr wedge d theta. I mean, that's just taking, first of all, when you take dx wedge dy, you get two non-zero terms. This term wedged with that term is 0 because you have two drs. This term wedged with that term, you have r cosine squared dr d theta. This term wedged with that term gives you minus r sine squared d theta wedge dr, but changing the order of the d theta and dr gives exactly this times the sine squared. And then you have cosine squared plus sine squared, which is 1. And you end up with that. And you'll note here that in polar coordinates, you have grr equal to 1, and you have g theta theta equal to r squared. So indeed, g bar here is r squared, because that's the determinant. You also have gr theta equal to 0, right? So indeed, what is in front here is the square root of the metric determinant. So that all works out very nicely. So finally, to mention, because we were discussing the exterior derivative and we were discussing integration, I want to just mention what is called the Stokes theorem. So you are probably familiar with the typical Stokes theorem of vector integration in 3 dimensions, but this is actually a more general Stokes theorem that includes that theorem, which is also called the curl theorem. So we let omega be a p-form and capital omega a p plus 1 dimensional submanifold. So essentially a p plus 1 dimensional region in your space. Then the following statement holds, that if you integrate over omega the exterior derivative of this p form, then that is equal to the integral over the boundary of the region of omega. And we saw last time that this d omega, depending on in 3 dimensions, depending on p, we saw that it could be the gradient, it could be the curl, it could be the divergence, and so on. So it turns out that this statement here, this theorem, includes a lot of well-known theorem. For example, it's Green's formula in the plane. It's the fundamental theorem of calculus. It's the divergence theorem, and it's the curl theorem, and many more, right? So depending on the value of p. I'm not going to prove this because then we would use all of this lecture to do that. If you're interested, you can find the proof on pages 580 to 583 in my book. So it's relatively straightforward to prove, but it takes a lot of time to set it up. So therefore I will not do that now, just to tell you that this theorem exists. And well, you know that these are very powerful theorems each in themselves, but this includes all of them. And you see that the kind of idea is the same as in all of those. You have something that you integrate over a boundary, and then you get that this is equal to the integral of the entire region of some derivative of that. For example, think of some closed surface. You integrate something over a flux over a closed surface. You get the integral over the bounded region of the divergence of that, right? And that would be the corresponding thing to the divergence theorem. Right. Any questions? If not, let's move on. So we come to what I was thinking of, what I was planning to discuss today, which is to return a bit to analytical mechanics, the Lagrange formalism, as well as the Hamilton formalism. Let's see how far we get, and to express those in terms of what we were discussing last week. So let's revisit the Lagrange formalism. So you remember in the Lagrange formalism, what we did was that we had some generalized coordinates that we used to write down a Lagrangian that we used to determine the action, and then we extremized the action. So this space, the space described by n generalized coordinates we call the configuration space. So essentially, a point in configuration space is a possible configuration of the system. You can determine that by giving n coordinates. For example, if you have something like the double pendulum with m1 and m2, you could give the two angles here as your coordinates, and those would be describing your generalized space. In this case, a two-dimensional space, right? So I'm going to call this configuration space, I'm going to call it M, just as we did last week. Now, the Lagrangian is not only a function on configuration space, right? Because you have terms like the kinetic term. What it is a function of, Lagrangian is a function L from Tm to real numbers, and I'm going to define what Tm is briefly. So Tm, that's the union over all points in M of the tangent spaces. So essentially, it's just saying that an element of Tm is a vector somewhere on this configuration space. So we can use this to describe not only where in configuration space we are, but also how fast we are moving somewhere. So if your configuration space, for example, was a sphere, an element of Tm here would be, for example, a vector at point P. And that vector could be describing, for example, your velocity at some time. But it could also be a vector at any other point, say Q. This is another element of the tangent of the this Tm. This Tm is called the tangent bundle. So it's a vector along with its position. Okay, the typical Lagrangian is on the following form, that L, well, is equal to 1/2, and then you have some function of velocity, which we typically call kinetic energy, right? Let me just write that first. Let me write T minus V, where V is the potential and T is the kinetic energy. The kinetic energy is typically 1/2, and then you have some inertia, and then you depend on the direction that you're moving and how fast you're moving. So essentially, you depend on the vector here itself, right? So it's some function taking essentially squaring a vector. So if I act here on some vector x, it's m of x and x, that's your kinetic energy. X is the vector. And then minus this v, the potential is a function only on the generalized coordinates. So it doesn't depend on the vector itself, it just depends on where the vector is. So we usually call this this function pi is the projection function and we say that pi of x is equal to p if x belongs to the tangent space as P. It's essentially just taking one of those vectors and mapping it to the point where the vector exists. So evaluating this along a curve, some curve gamma, we would have that L is a function of the tangent vector of gamma, and that depends on on time t. That's 1/2 m gamma dot minus v of the projection of gamma of t, or rather gamma t, because that's where gamma dot exists, right? If you want to write this down in coordinates, this is 1/2 mij, let me use a and b instead, mab, let me name the coordinates q, qa dot, qb dot, minus v, and v depends only on the coordinates q. And I want you to know that in general here, this m is a rank 2 tensor. It can depend, the components can depend on the position q as well. Okay, so what happens now is the following. So what you write down, we write down the action. Which we call S as the time integral of the Lagrangian of gamma of t dt. And then we extremize that action. And if you do this extremization, extremizing the action and you follow through with all of the maths, what you get is that this M is a rank 2 tensor, and it maps two tangent vectors to a number, but equally well it can be seen as a map from a tangent vector to a dual vector, right? Because if I leave this argument free, that's a position where I should insert a vector, so it's a map from vectors to numbers. So if I just insert something here, that's going to be, if I just insert something in the second argument, that's going to be a dual vector. And what I need to insert here is the covariant derivative in the direction of the function of the velocity itself. And this must be equal to minus dv. So the differential of this function v, the potential. But this looks oddly familiar, right? So this function here is essentially what we would call an acceleration, a. And it's a vector, right? So because it's how the velocity changes as time progresses, right? So this is acceleration by definition. And then we have some inertia here. It's a rank 2 tensor, but it's some inertia, and it's equal to minus some derivative of the potential. So this is essentially just a generalization of Newton's second law. So essentially you have mass times acceleration is minus the derivative of the potential. You could of course define this as f. F would be a dual vector. Okay, any questions on that? Okay, so there is an example with a spherical pendulum in the, well, let me take that example actually, because I want to use it later on. So a spherical pendulum, that's essentially, you have a sphere and you have a gravitational field and you have a particle moving around on this sphere under influence of this gravitational potential. So in this case, the components of the tensor M would be given by the mass of this particle times the radius of the sphere times GAB, where GAB here are the components of the metric on the unit sphere. So the sphere with radius 1. And you can imagine that this is the case because if I write down here the kinetic energy, so T here would be 1/2 mr squared, and I will have theta dot squared plus sine squared theta phi dot squared, where theta and phi are your typical spherical coordinates. Okay, so that's the kinetic energy. What about the potential energy? Well, the potential energy is given by mgh, So in this case, if I write it down in coordinates, it's minus mgr cosine theta. This is a function on configuration space itself. It's only a function of the coordinates, in this case just the coordinate theta, not the function of the derivatives of the coordinates. So this means our Lagrangian L, it's 1/2 mr squared theta dot squared plus sine squared theta phi dot squared minus this d, so plus mgr cosine theta. Okay, what about the v? So if I just take the v here, well, it depends only on theta, right? If I differentiate cosine theta, I get minus sine theta. So it's mgr, which are just constants, and sine theta d theta. And then I can use this to write down the equations of motion just using this generalized this generalization of Newton's second law. So if I do that, essentially what I get is theta double dot minus 1/2 sine 2 theta phi dot squared. That's equal to minus gr sine theta and phi dot dot plus 2 cotangent theta phi dot theta dot. That's equal to 0. So this would be the component in the theta direction, and this is the component in the phi direction. These terms arise because of the Christoffel symbols appearing in this derivative. Okay, we have 7 minutes left before the break. I want to finish our discussion on Lagrange mechanics by a short discussion on Noether's theorem. And how it appears in this formalism. So I'm going to assume that there is a transformation of a configuration space generated by some vector field K, right? So how vector fields generate transformations through their flows. But not only that, I want to say that under which the action is invariant. So I want to have, if I take this dt, that's equal to, if I perform the transformation. So if I take the flow here, I get the same thing. So the action is indeed invariant under this transformation. Then Q equals to this m k gamma dot is a constant of motion. Okay, so what does this mean? Well, in particular, let's look at the case when this is true. So we have actually a true symmetry. So the Lagrangian before and after the transformation is the same. Okay, but if this should be the case, then I know that 1/2 m gamma dot minus v of gamma, that must be equal to 1/2 m of these transformed gammas minus v of gamma sk gamma. Okay. But for this to be true, then m of gamma dot must be equal to m of this transformed, right? Gamma dot, it's a lot of writing. But just by the properties of the push forward and pullback, I can write this as gamma minus sk of m of gamma dot. And this should be true for all gamma dots. It should be true for all curves. But this is only true for all curves if this tensor is the same as that tensor. This tensor m is equal to the pullback of m. But that's only true if the lead derivative of m is 0. So I get that the lead derivative of m is 0. So indeed, this k is a killing field of what is called the kinematic metric, this m. But in addition, the potential terms must also be equivalent. So we have v of gamma must be equal to v of the pullback of gamma. But we can do the same thing here. This is equal to minus sk v, it's just the pullback of the function of gamma itself, and this means that v is equal to gamma minus sk of v, or the killing derivative of v, which is just k acting on v, must be equal to 0. Okay, so we saw now for to have a true symmetry like this, we must have these two conditions fulfilled, right? So if that is the case, well, we have seen that if in the case of v equal to 0, we have seen that this indeed fulfills it. We discussed it last time, that then this is a constant of motion. And there is, I did not define that as an exercise last time, but I will leave it actually as an exercise to show that when you introduce an additional potential, so you have this additional term here in the equations of motion, then indeed you will still preserve this quantity. You prove it essentially exactly the same way as you would for a killing field only. Okay. So that's the theory. I mean, just differentiate this and see what comes out when you use the equations of motion. Under the requirement this is 0 and that this is 0. And you'll see that you get that this is indeed a constant of motion. So just an example of that, we go back to the spherical pendulum, and you'll note that the spherical pendulum indeed has a symmetry like this. So we saw that m here was m r squared the theta tensor, the theta plus sine squared theta d phi tensor d phi. And we also had that v was minus mgr cosine theta. So as you can see, the components here, the 1 and the sine squared theta, they do not depend on phi. So we know that k equal to d phi is a killing field. And indeed, k acting on v, so d phi acting on minus mgr cosine theta, well, cosine theta does not depend on phi, so this is indeed 0. So this field d phi indeed is a symmetry of this spherical pendulum. If we look at the quantity m k gamma dot, what is that? Well, k was d phi, so we have m r squared. If I insert d phi here into the first argument, that is equal to 0 here, because the theta d phi is 0. And then I have a sine squared theta from this, and I get a 1 from inserting the phi there, and I have the theta left. So it's the phi gamma dot. But the phi gamma dot is just by definition phi dot. So what we get out of this is m r squared sine squared theta phi dot. So if you want to physically interpret this is the angular momentum around the vertical symmetry axis. And it's also exactly the conserved quantity you would obtain if you look at this from the Noether theorem point of view, right? So this is Noether's theorem expressed in a slightly more formal way. So before the break, we discussed the Lagrangian version of Noether's theorem, a bit more formalized using the mathematics that we discussed last week in terms of derivatives on more general spaces, and using the covariant derivative and using this kinematic metric. So what I want to talk about this hour is essentially the corresponding thing in Hamilton mechanics. So I'm going to talk about the symmetries in Hamilton mechanics, how they are described, and how we can use them. We'll also see a little bit how it's a little bit, even perhaps a bit more general than in the Lagrange case. But in order to do this, I first want to have a short discussion of when a continuous transformation is canonical. So let's consider a transformation of the phase space variable. So phase space is what you have in Hamilton mechanics instead of configuration space as you had in Lagrange mechanics. On top of the coordinates that tell you where you are in phase space, you have additionally as many coordinates telling you how fast you're moving somewhere. So essentially the generalized coordinates of your configuration space, n of those plus n velocities or momenta. So we consider a transformation of the generalized coordinates qa going to some new coordinate, and I want to have a continuous transformation, so I want to first consider the infinitesimal version of that, so epsilon times delta qa. It should be noted here that delta qa can be a function of both of the generalized coordinates and the momentum. And at the same time, the momenta go to new momenta PB, which are equal to, sorry, I missed a little bit here. This should be equal to QA plus that. Sometimes it goes a bit fast. My new canonical momenta should be the old canonical momenta plus some infinitesimal addition delta PB. So in both cases, these deltas can be functions of both Q and P, both the generalized coordinates and the corresponding canonical moment. So what does it mean for this such a transformation to be canonical? Well, it means that the Poisson bracket is preserved. So if you remember the Poisson bracket, if we have two functions f and g, that's essentially the f, the qa, the g, the pa, minus the f, the pa, the g, the qa. So that's the definition of the Poisson bracket. The Poisson bracket being preserved, well, if we just take the coordinates themselves, so QA PB, that should be delta AB. If you take the Poisson bracket between two generalized coordinates, that's 0, and that's the same as if you take the Poisson bracket between two of the canonical momenta. So if you have this situation and we say that your coordinates are on canonical form, and the Poisson bracket being preserved essentially means that the Q's and the capital Q's and the capital P's should also fulfill this. So in particular, if I take the Poisson bracket between capital QA and capital QB, then and I keep now only terms linear in epsilon, not going to care about terms that are higher order. So then I get, first of all, I get the QA QB from the leading terms, well, this QA and then the QB, plus epsilon, and then I take the delta QA from the first term and QB, plus QA delta QB, plus higher order terms, epsilon square. Okay. But if I write this out, well, the first term here is 0 because the original coordinates were canonical. I get an epsilon, and then I have d delta QB dp dpa, right? So this term comes from this bracket. If I insert QA as my f here, this is a delta. What I have left is the delta inserted there, and that's the dpa. And in the other term, I get a minus sign because I'm now having QB in the second term. So this is where I have the derivative that becomes non-zero. D delta QA dPB, right? Plus the higher order terms again, but I'm not going to care about those. So this means for this to be 0, to linear order in epsilon, this must be equal to 0, right? And I can do the same thing here for the p's, for the new p's. So if I take PA, PB, I follow through with the same computation. I get this minus epsilon d delta PB dQA minus d delta PA dQB, and this should be equal to 0. I wrote it already. So if that is equal to 0, then to linear order, that is equal to 0 as well, right? And finally, let's look at QA PB, which should be delta AB, right? If I should keep my canonical commutation relations. And the same story again. This is equal, well, up to linear order in epsilon. This is now equal to epsilon d delta delta Q delta PB, sorry, dPA minus, plus d delta QA dQB. And since this should be equal to a delta, plus delta AB. That comes from the commutation of this QA with that PB, right? So for this to be equal to that, up to linear order in delta, in epsilon, this must be equal to 0 as well. So now we have a lot of zeros, but all of those zeros, this 0, this 0, and this 0, they are fulfilled, are satisfied, if we choose to have the following. So if I put delta QA to be equal to the derivative of some function f of the coordinates both q and p, dPA, and delta PB minus the f dQB. If you can verify this. For example, if we insert these two here, okay, then the delta PB, we insert that's minus the f dQB. So we have minus the second derivative of f the PA dQB. While at the same time, if we insert this here, we get the same thing but with a plus sign, so it's indeed 0. You can verify in the same way that these two are indeed going to be 0. We assume, of course, here that all of these derivatives commute. Okay, so f here is an arbitrary function. Whatever f I put in, I get one of these canonical transformations. But you'll also see that, this here that's just QAF, if you will. And this here, the P derivative, that's PBF. So if I want to write this in a slightly more general form, using coordinates YR. So YR are all of the coordinates, both the Q's and the P's. You can order them such that the first n coordinates are the Q's and the second n coordinates are the P's. But I can still write them in the same way. You saw that delta QA was QA, the Poisson bracket with F, and delta PB was PB Poisson bracket with F. So I can write everything as delta yr being equal to the Poisson bracket between yr and some function f. Right? So this is the infinitesimal form of the continuous transformation that's satisfying that y dot r should be equal to yrf, right? So this is called the phase space flow. Oops, sorry. This is called the phase space flow generated by the function f. Remember here, f is a function generally of both of the q's and the p's. So generally f is a function of all of the y's. And I'm going to introduce here now also just a bit of notation. I'm going to introduce omega rs as the Poisson bracket of yr and ys. So here you see that this is going to be plus minus 1 or 0. So if I take both y's to be q's, that's 0. If I take them to be both p's, it's also 0. If I take yr here to be one of the q's, then there is one of the p's, if I insert that as ys, for which is 1, and vice versa. If I take this as a p, then there's one q here for which is minus 1. This omega rs is it's an antisymmetric in the indices. If I change RNS, I get a minus 1 because the Poisson bracket is antisymmetric, and it's plus minus 1 depending on, or 0 depending on exactly which coordinates I put in here. So the flow satisfying this is called the phase space flow generated by the function f. Okay, and I mean, if you want to be a bit more mathematical, you can see that this is a tangent vector, right? In this phase space, because it's the derivatives of the coordinates, so it's a tangent vector. And so what is here must also be a vector. This omega here is essentially a map from dual vectors to vectors. What's on the left hand side is a vector, and this is something mapping dual vectors to vectors. The dual vector here in this case being df. Any questions right off the bat? If not, I'll take an example or two. So let me do that just to see how this looks like in action. So the first example, I'm just going to look at a one-dimensional motion. So one-dimensional motion. That means that I have a single configuration coordinate. So configuration described by x, and the momentum being the corresponding canonical momentum p. Okay, so for example, xp here is equal to 1, whereas xx is the same as pp, which is equal to 0. Okay, so what happens? Let me just see what happens. Let us use a function f. I need to define as a simplistic function f as I can that doesn't become trivial. If I choose a constant, for example, everything becomes trivial because there is no flow at all. But let's use f equal to p. That's a function of the phase space coordinates because it's p. P is a phase space coordinate, so this is a function of the phase space coordinates. It's independent of x. But let's see what kind of flow this generates. So this means that the x ds, that should be the Poisson bracket of x and f. Well, that's just xp. That's 1. So this implies that x, and for s equal to 0, I should have x itself. So I get x plus s. Similarly for the PDS, that's pf, but f was p. So that's 0, which implies that p doesn't change with this flow. And you can easily verify that this is indeed a canonical transformation. If I define this as my capital X and this is my capital P, you can easily verify that the Poisson bracket is still on the canonical form. Right? So in particular, we see that P here, the function P, generates translations in S. So you can think back now to when we talked about symmetries, when we had generators. This function P is the generator of translations in S, or translations in X. We can do exactly the same thing if we put f equal to x. Then we will just by the same math we will get translations in P. Okay. So here we just say that the function f equal to p is the generator of translations in X, and those are canonical transformations. To become a little bit more involved example, let's look at what is going to become phase space rotations. Let's keep to the same one-dimensional motion, but I can instead let my function f, I can define it as 1/2 x squared plus k squared p squared for some positive number k. Okay, that has the correct dimensions so that both coordinates have both terms in this have the same dimension. Okay, so what does this mean? Well, it means that if I take the x ds here for this transformation, it should be x xf. But x here commutes with the first term because the first term only contains the x's. So what I get here is 1/2 k squared as constant. I can pick it out, x p squared. That's 1/2 k squared 2p times xp, right? That's just the chain rule of derivatives. So what I end up with, the xp is of course still 1. So what I end up with is k squared p. Okay, I do the same thing for dp ds. That's pf. Now the second term commutes with p, so that's going to give you nothing. I get 1/2 px squared. Same thing again, the chain rule of derivatives, px, that's minus x. Okay. So now you have the differential equations for this flow in phase space, and if you solve this, you'll end up with an x that is x cosine ks plus kp sine ks, and well, x goes to that. Oops, I want to use this one. Whereas p maps to p, oops, cosine ks minus x sine ks divided by k. So you can see that this is a rotation in phase space. I could introduce a normalized momentum, which I normalized by this constant k, and it would just look just like a rotation. But this is a rotation in phase space, and it's a canonical transformation. So that's just two examples of canonical transformations generated by different functions f. Okay. So in particular here, you remember that this reminds us of something. You'll remember that that in Hamilton mechanics, the equations of motion were just these. You had dy yr dt equal to the commutator of yr with the Hamiltonian. Nothing really changes here because I used the time as the parameter instead of a generalized parameter s. I mean, if I put this in the form of p's and q's, this would be the qa dt equal to qa h, and the pa dt equals to pa h. Is of course just the same thing, just I wrote them all at once using this y notation instead. But this means that the time evolution is a canonical transformation generated by the Hamiltonian. And where the transformation parameter is time itself. So for example, if we look back here at the phase space rotations, this looks terribly much like the Hamiltonian for a harmonic oscillator. And indeed, what you have in the case of a harmonic oscillator is just something that oscillates harmonically. We have a cosine term and a sine term for both the position and the canonical moment. Okay, but if I have any function f now, so I can look not only at how the coordinates change with the parameter under a flow. I can also change, so given the flow generated by some function g now, we can ask ourselves how does the value of some other function f change when we follow this flow? Okay, so I want to know essentially what is the f ds when I move along this flow. But we can here use the chain rule for derivatives. So this is the f. This is a partial derivative. F is a function of the phase space coordinates. So we have the f, the yr, and then we have dyr ds, right? But this we can write as df dyr, and then the Poisson bracket, dyr with g, since we're talking about the flow generated by g. But now we can again use the Poisson bracket, the chain rule for derivatives in reverse. We can write this as fg, the Poisson commutator of f and g. Okay, so this means that f is conserved if and only if it commutes with g. Poisson commutes with g. Okay. So if this is the case, we say that G is a symmetry of F. But here's the funny thing, or rather it might seem rather straightforward when you see it like this, but the Poisson commutator is antisymmetric, right? So if the Poisson commutator between F and G is 0, so if this is the case, if Fg is equal to 0, then the commutator between G and F, which is minus Fg, is also equal to 0. So this means that if the flow generated by G is a symmetry of F, then the flow generated by F is a symmetry of G. I'm just exchanging the roles here between F and G. So in particular, if F generates a symmetry of the Hamiltonian, H, then the derivative of F with respect to time is equal to 0. So F is conserved. So you'll see how this is very close to what we said in the case of Noether's theorem, right? If we have some symmetry, then there is a corresponding conserved quantity. And in this case, the conserved quantity is the function generating the symmetry. So let's see if we can get Noether's theorem back. So I'm going to look at the correspondence here to Noether's theorem. Now you'll remember that when we looked at Noether's theorem in the Lagrange formalism, we were only looking at the transformations in configuration space. So we were only looking at transformation that changed the coordinates of configuration space into new coordinates on configuration space. This is a little bit more restrictive because here in general, these transformations, these canonical transformations that we're talking about here, these deltas can depend both on p's and q's. But if I want to just look at transformations on configuration space, I'm restricting this delta q to depend only on the q's, not on the p's. So that was the case that we should have in the Lagrange case. You'll see, for example, here that here my delta x was 1. Sorry, not here. Here the delta x is proportional to p. So this would not be a transformation only of configuration space. This is indeed a true phase space rotation. It rotates the momenta into the generalized coordinates and vice versa. But if I want to make that that particular restriction. So I want to have QA map into capital QA, which is equal to QA plus some epsilon KA, where KA here depends only on Q. It does not depend on the piece. Okay. But this means if we go back here, I should have the following, right? The function that is my generating function, its derivative with respect to PA should be QA. This delta QA, or KA in this case. So this means that KA, that's the derivative with respect to PA of some function f. But Ka itself does not depend on P. So for this to be the case, then my f must be equal to Pa times Ka. Right? Because if I take the derivative here with respect to Pa, I get Ka out. Because Ka does not depend on the piece. I can of course add an integration constant as well, but that's not going to do anything. Okay, so now I know that the function generating this is of this form. Okay, but this means that delta, that is going to map to capital PA, which is PA minus epsilon df dqa now. Right? This is what we should have. And if we write this out, this is PA, and then we get minus epsilon, and then dA Ka, because this is a derivative with respect to QA. Right? And the PA, sorry, this should be a B. I have to change the B, KB, PB. That's just inserting the definition of f here. Just changing the indices, the summation indices for B's instead. Okay, so this is the P transformation. Okay, so I now know how P transforms. So this means that I can look at what this means. So I can assume that this leaves the Lagrangian invariant. So I have some, on the Lagrange side, I have some transformation that looks like this, and that leaves L invariant, as we saw in the last hour. If that is the case, then under the transformation generated by f, I can compute what the derivative of the Hamiltonian is. Right? So I get a particular Hamiltonian if I have a particular Lagrange. Right? If we write that down, so if L is 1/2 MAB Q dot A Q dot B minus V, then the Hamilton function is 1/2 MAB PA PB plus V. So this is a function of the P's and the Q's, right? And this computation, I don't have the time to go into the detail. You can find the computation in the lecture notes. But sorry, let me just write out that this is equal to, of course, the HF, so PA KA. If you follow through with this computation, requiring that this Ka are the components of this killing vector field that we saw before the break, if that is a symmetry on the Lagrange side, you're going to get 0 here as well. So indeed, if we have a symmetry on the Lagrange side, it translates directly to a symmetry on the Hamilton side as well. So what we know then is that we have a conserved quantity, because the Hamiltonian commutes with PAKA. So PAKA must be conserved under time evolution of the system. So F equal to PAKA is a constant of motion. And if you now do the express the canonical momentum in terms of the q dots and the q's, so with PA, that's MAB q dot B, then then this F, that's KA MAB q dot B, and this is exactly the same quantity that we saw should be constant before the break. So it's exactly this very same conserved quantity. That shouldn't come as a surprise. Of course, the Hamilton and the Lagrange formalism are equivalent in this situation. So if I have a conserved quantity on the Lagrange side, I should have a conserved quantity on the Hamilton side as well, of course. Well, it becomes clear that it is indeed the same. So I just wanted to show you that when we have this correspondence between the Noether theorem on the Lagrange side and the corresponding statement on the Hamilton